Hey everybody, it's Mr. Canfield. Today we're doing indefinite integrals day 2 or part 2 or whatever. So I did the first video, here's the second one. So we're going to start out and we're going to talk about a special integral named e to the x dx. Well, let's think about this. Remember, when we're doing integrals, we're really asking ourselves, what function do I take the derivative of and get e to the x? So if I take the derivative of e to the x, then I get e to the x. And then remember, we add this, we call it the constant of integration. Wow, constant of integration, so the plus c. Because remember, when we take this derivative, the derivative of a constant is 0, it goes away. So there's another special integral, the integral of e to the x squared dx. And it turns out that we can't do this integral. So you are going to come across things in integrals that don't have answers. It almost never happens in this course, but it is possible. So the first thing that I wanted to say kind of out of the gate with this is derivatives are pretty straightforward. We have a set of rules and we use them. Integrals can be much more puzzling. And so we're gonna go through a bunch of techniques that we use to try to figure out what function we take a derivative of to get the thing we're looking at. So we'll start with some simpler ones and we'll move into more complex, but here we go. So the first one we see, it's number 16 in the notes. It says the integral of 2x minus 3 squared dx. So at the outset, I've got a function squared, and trying to figure out, okay, what did I take the derivative of to get this could be very challenging. Instead of going through, kind of going backwards, well, the 2 is going to become a 3, but then there's chain rule that's happening, and how do I undo chain rule? Instead of having to worry about all that, it's going to be so much easier for us to FOIL this out. And I'm foiling this out like this because I'm not assuming that you remember how to square a binomial easily. If you think this is 4x squared minus 9 or plus 9, you're fired. Not really, but fire that part of your brain because it's so wrong. It says 2x minus 3 squared. This means take this times itself twice. So every time you do this, there's a little puppy that's crying somewhere going, why'd you do that? All right, anyway, over here, if we FOIL this out, and FOIL is an inappropriate term I really should use, if we simply multiply these two binomials using the distributive property. All right, anyway, so 2x times 2x gets us, let me write the integral symbol still. I haven't taken the integral yet. So we get 4x squared, and then 2x times minus 3 is minus 6x, then negative 3 times 2x is minus 6x, and then negative 3 times negative 3 is plus 9 dx. So that's just the integral of 4x squared minus 12x plus 9 dx. So our antiderivative of this, we can just go term by term. Remember that we keep what we have. So it's x to the 2. We're going to raise the exponent. We're going to add 1 to it. Remember, we're reversing everything. So we're adding 1 to our exponent, and then we divide by our new exponent. And then minus 12x. So our current exponent is 1. So when we raise it by 1, we get 2, and we divide by our new exponent. And then we raise this by 1. Oh, wait, sorry, there is no number here. There is no x here. The derivative of something gets us 9. That would be 9x. And sure, you could tell yourself that it was an x to the 0 that was secretly hiding there. Divide by our new exponent of 1, and divided by 1 doesn't do anything. Then add the plus c. I would mark this correct, even though it'd be more appropriate to simplify that. And remember that 4x cubed over 3 can be written as 4x cubed over 3 or 4/3 x cubed. These are equivalent statements. So a lot of my students, and me included, especially when I was in high school, I struggle with 4x cubed over 3, but 4/3 x cubed makes sense to me. So if you remember that these are synonyms, it helps. So I think one more thing to talk about this is 2x minus 3, if I'm trying to square it and I want to use the trick actually does start with this 4x squared and this plus 9. You just have to remember there's a middle term, and the middle term is the product of these two doubled. So 2x and 3 is, or negative 3 is negative 6x. Double that, you get negative 12x. And you'll see that that's what I got there. So this strategy always works. With squaring, cubing it's different. You have to use Pascal's triangle, but anyway. Key thing is we got our 2 different acceptable answers for this integral. All right, number 17. I guess I can just do this. Yeah, okay. So 17, I see the integral of x squared plus 3x plus 1 over x to the 4th dx. All right, so we look at this, and taking the derivative of this, we would, a lot of us would just jump straight to quotient rule, and others of us would notice that we are actually capable of taking this fraction and breaking it apart. And doing this is far and away better. I know it's not good for us to use subjective language like better and worse, but taking the integral of this is actually very, very challenging and potentially impossible, because I don't know how to do something. Like, what derivative is going to give me this? I don't know. I can't just look at this and know. I mean, did I do quotient rule to get here? If I did, like what was the bottom? What did it used to be? What was the top? How did this work? Instead of all that, break this apart, do some simplifying. Well, x squared over x to the 4th, this is xx and this is xxxx, right? So 2 of them cancel. We have 2 left on the bottom. This is 1 over x squared. We're going to have, one of them are going to cancel, and there's going to be 3 left on the bottom. And then, oh, this is just chilling. Here's the problem. You still might not be sure how to take an antiderivative or an integral of any of these. But remember, this is x to the negative 2. This is 3x to the negative 3. This is x to the negative 4. And now we can simply use our power rule for this, where we take the power and we add 1 to it, so that's x to the negative 1, and then divide by our new exponent. So plus 3, x to the, add 1 to that, negative 2, divide by our new exponent. Add 1 to that, so x to the negative 3, divide by our new exponent, then add a plus c. So I'm going to clean this up, but that's it. So the first bit of cleaning we can do is all these negative exponents can drop down to the bottom, and I'm going to put the negatives out front. So I'm going to say this is negative 1 over x minus 3 over 2 x squared minus 1 over 3x cubed plus c. So a big bit of mess, but if we were to take the derivative of this and simplify it, we would get our original expression. All right, let's look at number 18, a fancier version of the same principle. So 6x squared, so I should write it big just in case you can't see. If you are viewing this on a mobile device. All right, so we've got 6x squared minus 11x minus 10. Oh, and you might notice I have kind of a format for how I write my work for these. I'm writing the integral symbol, and then I write equals, and I write my first step. And until I actually take the integral, I leave the integral, and I call it the integral sandwich, because we have the integral symbol and the index of integration, kind of with all the stuff in the middle that we're actually taking the integral of. So boom, 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 boom. Now I actually integrated. So for me, I like this, and then I have a nice space for side work over here. So that's generally how I do these, or especially as a teacher trying to show my steps and show my work. So let's see. There's kind of 2 things happening at once here. This square root of x is the same as x to the 1/2, right? So I can say 6x squared over x to the 1/2 minus 11x over x to the 1/2 minus 10 over x to the 1/2 dx. So the far right one's the easy one. It's just minus 10x to the negative 1/2. This one, though, these other two, so 6x squared and x to the 1/2. Remember, we are subtracting exponents when we're dividing like this. So if I divide that, 2 minus 1/2. Well, 2 is 2 over 1. I need to make this over 2. So I'm going to do times 2 over 2, right, and get 4. This is 4 halves. That's 1 halves. 4 minus 1 is 3. So I can call this 6x to the 3 halves. Same thing here. This is 2 halves minus 1/2 is 1/2. So now, when we integrate this one, forgot the integral symbol, haven't taken the integral yet. Now I've taken the integral, I get 6x to the, add 1 to that, we get 5 halves. And I remember, dividing by 5 halves is yucky. So instead we can, that's a technical term. So instead we can instead of dividing by 5 halves, we can multiply by 2 over 5. Same thing here, 11x to the 3 halves. Instead of dividing by 3 halves, we can multiply by its reciprocal. And then next to the, add 1 to that, we get 1/2, multiply by 2 over 1, plus c. So here I'll get, oh, I was going to say 2 times 6 is 10, and then it simplifies. Silly. 12/5. All right, 12 over 5, x to the 5 halves, minus 22/3, x to the 3 halves, minus 20, x to the 1/2, plus c. And sure, I could rewrite these as square roots. There's no real need to, but just maybe for the sake of clarity, x to the 5 halves is the square root of x to the 5th, because the 2 is the little index guy in there. So you could say this is like 12 or 5. Like, you could write it like that if you want to, you know, look fancy. Look at how fancy I am. So let's see what comes next. Trig, right. So what we want to do is we want to build from derivatives and go to integrals. So we have sine, cosine, tangent, cosecant, whoops, CSS, that's the school that we're at. CSC, so SEC, COT, all right. So for the derivative of sine, so here's f prime. The derivative of sine was pause. Do you know these? Do you remember them? It's not magic. If you don't remember them, go figure them out. This is so important, and by so important I mean on the AP exam, if they're not just easy, if you don't just know them like you know the real name of your favorite character on a TV show because you've IMDb'd them and you know everything about them and you follow them on Facebook. It's not magic about you knowing those things. You've just spent time learning them. So if you don't know the derivative of sine is cosine. If you don't know the derivative of cosine is negative sine. Tangent is secant squared. Cosecant is negative cosecant cotangent. Secant is secant tangent, and cotangent is negative cosecant squared. I don't know these because I'm special, or because I'm smart, or because I'm a math teacher. Like, I know these because I spent the time with them to memorize them. That's all it is. So anyway, knowing this, we can say, hey, what's the integral of cosine dx? What did I take the derivative of to get cosine? It's sine. What about okay. So instead of saying what's the integral of negative sine, what if we just had the integral of sine on its own? Well, the integral of sine on its own then would be cosine. Oh, wait a minute though. I forgot the plus c's. What's the derivative of cosine? It's negative sine. So that means that the integral of regular old sine would actually be negative cosine. Because if that negative wasn't there, then when we take the derivative of this, we would get a negative sign. Now when we take this derivative, we get negative sine, which is just positive sine. So now we know the integral of secant squared. The integral of secant squared is just tangent. And same thing here. Let's cross out those negatives. So the integral of cosecant cotangent is going to be negative cosecant. And the integral of secant tangent is just going to be secant. And the integral of cosecant squared is just going to be cotangent, with a negative on it, plus c. So memory device for you. These are just reverse derivatives, but the other thing is the negatives all come from, or all the ones that start with a c get a negative. Okay, I don't actually use that memory device. All I think about is that with the derivatives of these, my memory device was the derivatives of these, the ones with c's, you get a negative. So yeah, if you have to go look this up every time, then you haven't done it enough. And when you have to go look it up, I would strongly urge you to go, like for number 19, it says the integral of 4 sine x. If you're like, I forget what the integral of sine is, I think it's this. You want to ask yourself, you want to try to think what it is before you go look it up, because the act of correcting ourselves is more beneficial to just giving ourselves answers. So what I'm going to do for this actually before I take the integral is I'm going to pull the 4 out. It's a constant times an integrable function. So 4 sine x. Oh, well, so the antiderivative of sine is just negative cosine. So I can say this is negative 4 cosine x plus c. To number 20. Number 20 says negative 2/3 cosine x dx. We're going to take the integral of that. So again, there's a constant out front. We can pull a constant out front of the integral. It's just got a cosine dx in there. Well, I took the derivative of sine to get cosine. So I can just say it's negative 2/3 sine x d. Ugh, keep writing that dx right now. I don't know why. All right, 21. Where does this end? Okay, there's a little bit more. Oh. Six over cosine squared x dx. You might look at this and immediately go, this is none of the ones that we talked about, until you remember that cosine is just, or 1 over cosine, sorry. 1 over cosine is the reciprocal of something. So 1 over cosine squared, I could rewrite this as 6 times the integral of secant squared dx. Remember that reciprocals never start with the same letter. Derivatives never start with the same letter either. That's a helpful memory device. So we're here. And I took the derivative of tangent to get that. So it's 6 tangent x plus c. 22, 9 cosine minus 4 sine. All right, I'm going to jump to the answer, and then I'm going to talk about like the technicality of what we're doing here. So 9 cosine, I took the derivative of 9 sine to get that. And then here it says minus 4 sine. That means that I started with a regular cosine, right? Because cosine turns into negative sine when we take its derivative. So I'm going to say plus 4 cosine x dx. I keep writing the dx, plus c. So the technicality of this, I actually could rewrite this as the integral of 9 cosine x minus the integral of 4 sine x. Wait, this has a dx, and then this has a dx. And then I can pull the constants out and say this is 9 integral cosine x dx minus 4 integral sine x dx. And then this is 9 times the integral of that, which is sine of x minus 4. The integral of this is negative cosine. Then we'll tack a plus c on the end because there could be some combination of constants added on. Or you could even have a plus c in both of them. But and then this cleans up to that answer. But if you kind of get what's happening here and you're just reversing derivatives in your mind, then you're really going to be fine. So that is my recommended way of approaching that. So not this. But again, if this was not working for you, then you can do this and use properties of integrals to separate and make things make more sense. So all right, let's see what's next. All right, we got 2 more. Negative sine x over cosine squared. And then 3 theta squared minus 2 cosecant squared theta. All right. All right. So in our first one, we look at this and we go, okay, I don't recognize anything. But I could rewrite this as negative sine over cosine times cosine. And then think about it. Well, sine over cosine is tangent. Let's say this is negative tangent. And then 1 over cosine is secant. Oh, this is tangent times secant. Secant times tangent, secant tangent. That is one of the derivatives that we know. Secant tangent is the derivative of secant. So I could actually say this is, and it had a negative already, so I could say it's negative secant x plus c. So if we can manipulate this, and it's not always apparent, that's what it was this time. Every problem's a little bit different. Let's look at this example. 3 theta squared, oh, but d theta. So theta is our x. Theta is our index of integration. So the integral here is just going to be, well, 3 theta squared. You add 1 to the power, divide by your new power. Oh, so we just get theta cubed. Here, minus 2 cosecant squared d theta. Well, what did I take the derivative of to get cosecant squared? It's cotangent. So it's just going to be, oh wait, but cotangent makes it negative. So it's already negative, so we can just use a plain cotangent. And that's it. So that's kind of the introduction to how we think about trig. So now we're going to solve what's called a differential equation. Sounds super complicated, I know. I know that, let's see, 25 says that f prime of x is equal to 3x minus 1, and that f of 2 is equal to 3. So we're wanting to find f of x. Well, if f prime is the derivative of f of x, then if I take the integral of f prime of x dx, I'll get f of x. So there's a property that we're allowed to use where if I do something to one side and I do it to the other, we still have a balanced equation. So I can actually integrate both sides of this. I don't normally write all this. What I normally just go is I'll go, oh, well, I know that f of x then, oh, there's a plus c here, isn't there, is equal to, the integral of this is going to be 3x squared over 2 minus x plus c. So we're going to do something kind of funky here. This says plus c, this says plus c. These are what we call arbitrary. They could be any number ever. We could even call this one c1 and c2. We're not sure what they are. We don't care what they are. If I take their derivative, I get back to here because they're both zeros. Oh, excuse me, when we take the derivative. So what we'll do is we're actually going to subtract c1 from both sides, and so c2 minus c1. We're not going to go through all that every time, though. We're just going to get in the habit of saying, look, yeah, there was a constant on both sides, but I can collect that constant over to either side. It's irrelevant, and I'm just going to call it a single plus c. I'm not going to say c1, c2, c3. I'm just going to say there's a single plus c on the end here. So now that we're here, we're like, we call this the general solution. To the differential equation. But we want what's called the particular solution. Oh, he's calling it the specific solution, but particular, specific. I've usually heard it called the particular solution. Whatever. That means, hopefully you understand. We're saying we could have any of these functions, take the derivative of it, you get 3x minus 1. But there's only one function, one specific or one particular function where when you plug in 2, you get out 3. So let's try that. When we plug in 2, we get out 3. So 2 goes in for x, 3 goes in for y. There's only one potential c value for this that makes this actually work. So let's see, 2 squared is 4. So it's 12 over 2, which is 6. 6 minus 2 is 4. So c is negative 1. So the only function that has 3x minus 1 as its derivative and f of 2 is equal to 3 is this specific particular 3x squared over 2 minus x minus 1. And this is called the particular solution, or as Stu calls it, the specific. So there we go. And that's all that's going on with these. So let's finish these out, and that'll be our indefinite integration chapter. So let's see, f prime is equal to x squared minus 2x plus 2. We know that f of 3 is equal to negative 1. So if I integrate both sides, I can say that f of x is equal to the integral of x squared minus 2x plus 2 dx, right, the integration. So then I can say that f of x is equal to x cubed over 3 minus x squared over 2, but there's a 2 already, so I'm just going to say minus x squared plus 2x plus c. And that's f of x. So now I can say, well, when I plug in 3 for x, what do I get? I get negative 1 for y. This is our general solution, and we'll find our particular solution now. Let's see, so 3 cubed is 27, right? I'm plugging in 3. So 3 cubed is 27, divided by 3 is 9, minus 9 plus 6 plus c. The 9's cancel, subtract the 6 from both sides, you get negative 7 is equal to c. So I get f of x is equal to x cubed over 3 minus x squared plus 2x minus 7. All right. Cool, next one's really good. 27 says f double prime is equal to 2. So if I want to integrate this, what's the integral of f double prime? What did we take the derivative of to get f double prime? We took the derivative of f prime, so it's actually going to be f prime of x is equal to, and then the integral of this is going to be 2x plus c. Oh, but it tells us that f prime of 4 is equal to 0. So we'll actually be able to solve for this c value right now. So I get 0 out when I plug in 4. So I get 8. So negative 8 is equal to c when I subtract 8 from both sides. So I could write this as f prime of x is equal to 2x minus 8. Because my goal is to actually find f of x, not just the next one up. So when I take this integral, I get f of x is equal to x squared minus 8x plus c. This is the way I usually won't even write the integral symbols and stuff when I'm doing the workout. When it's something that's as nice as this is, because this 2x is to the 1, we add 1 to that exponent, we get x to the 2, we divide by 2, and so the 2's cancel. And then constants are nice, and then there's a plus c. So then it tells us that we know f of 4 is equal to negative 1. So we can plug in negative 1. So 4 gets plugged in there, it's 16 minus 32 plus c. So that's negative 16. Added to both sides, we get 15. So I can say that f of x is equal to x squared minus 8x plus 15. All right. I usually want to skip his last examples, but they usually contain something interesting for us to look at here. This one says f double prime of x is equal to 2x. So then that means that f prime, when we take the antiderivative, when we take the integral of this, we just get x squared plus c. And we know that f prime of negative 3 is equal to 0. So we get 0 out when we plug in negative 3 here, and we get 9. So that's negative 9 is equal to c. So I can say f prime of x is equal to x squared minus 9. And then when I take the integral of that, we get x cubed over 3 minus 9x plus c. And it says plug in negative 3 and you get out 10. Negative 3, when we plug it in, we do get negative 27 here. Divided by 3 is negative 9. Then negative 9 times negative 3 is positive 27 plus c. So this is 10 is equal to 18 plus c. Subtract the 18, I get negative 8. So our function is x cubed over 3 minus 9x minus 8. And then our last one, 29. And I know I'm kind of rushing. So let's make sure we slow down for this last one. It's bound to be a little different. Let's see. It says, given that the graph of f passes through the point 0 pi, which is another way of saying f of 0 equals pi, and that the slope of the tangent line to f, that means that f prime of 1 minus sine x, find f of pi. So if we find the general solution to this by taking the integral, we'll get f of x is equal to x. Now, what did I take the derivative of to get negative sine? Be regular cosine. I know that f of 0 is equal to pi. That means that if I plug in 0 here, I get pi out. So let's see, 0 plus, cosine of 0 is 1. So I get pi is equal to 1 plus c. So c is equal to pi minus 1. Ew. Okay. So that means that I can write f of x is equal to x plus cosine of x plus pi minus 1. That sounds terrible, but f of pi is pretty nice. When I plug in pi, I get pi plus cosine pi plus pi minus 1. And sure enough, I thought these two things were going to cancel each other out. They don't. But cosine of pi is equal to negative 1. So we have pi minus 1 plus pi minus 1. We could write 2 pi minus 2. Yum. 2 whole pies. So yeah, this should give you enough to go off of to do really all these. Yeah. So, cool. Hope this was helpful. Bye!